So welcome to this afternoon session. The first thing to remind you is how to actually ask questions for the paper. So remember, there is this automatic system, Slido. You can ask the question there. The event code is ICCV2019_D2. So make sure to use this event ID to ask the questions. And we have already one question, for example, for this session. And we will be asking the question according to paper ID.
Also make sure that the two-digit number is the paper ID. The next four-digit numbers are the starting time of each presentation. Please do not be confused.
Okay, so with this, welcome to the video and action understanding session. I am Laura Leal-Taché, together with my colleague Bohyun Han. We are chairing this session. We have an exciting lineup of speakers for this afternoon. So remember, the presentations are 5 minutes long, and after three presentations, 3 papers, we have questions for 3 minutes. So make sure to write down your questions for the 3 papers, and this will be asked at the end of the small session.
All right. The first paper of this session is titled as GradNet, Gradient Guided Network for Visual Object Tracking. Okay, please start the presentation.
Hello everyone. My name is Dong Wang from Danelljan University of Technology. On behalf of my co-authors, I'd like to introduce our work, Gradient Guided Network for Visual Object Tracking. This is a work with University of Sydney and China Science in Telecom Technology. According to the tracker requires online update or not, there are usually can be two categories. The first one is only use the visual cues of the first frame. The second one is dynamically update the target features or model parameters. Here is an example. Both of them have advantage or weakness. Such as the first one, the models without update. Sometimes it will be less accurate but fast. The second one is online update target feature or model parameters. This manners usually considering the tracking as an online learning process. So it may be capture the target variation of the object. It usually more accurate, but usually slow. Here are some related works. The former one ignores some target variation, and the later one need more computations. But our goal is to achieve adapt to target variation or less computation in the meanwhile. We think we can use both advantage from these two methods. Here is an example. We found that gradient contains much discriminative information to distinguish the object from background or some similar instance. So we need to update with gradient. Usually, the trackers use gradient update need many iterations. If we use only one path BP, it is insufficient. So our motivation is one path BP of by network. Here is our framework. So given the initial feature embedding, we calculate its gradient and back propagation, and then end with the initial feature F2. Wait a moment. So, and send it into the subnet week again and obtain the new templates beta star. The beta star is our templates after update. This framework is quite simple, so you only need to calculate the gradient data and use a learning subnet U2. We also propose a template generation generalized method. Usually such training process need one-to-one corresponding like left figures. We relax this constraint. Here's our result on OTB dataset. The blue dot line is our baseline SAMS FC. We can see that our method can improve the baseline by a large margin. Here's our code. Here's our results on TC128 and VOT 2017 datasets. For more details, you can email us or scan this code. Our post ID is 20, code available here. So please see you in the coming post session. Thank you.
All right, next paper is FAMNet, Joint Learning of Feature, Affinity, and Multidimensional Assignment for Online Multi-Object Tracking.
Hello, everyone. So the title for our paper is FAMNet, so Joint Learning of Feature, Affinity, and Multidimensional Assignment for Online Multiple Object Tracking. So my name is Haibin Ling. So this is a paper with my student Peng. So he cannot attend here due to visa issues, unfortunately. Okay. So for multiple target tracking, in our setup, the input is an image sequence and some detected candidates. And the desired output should be the trajectories of all the targets across the time. And for typical multiple object tracking algorithm, there are usually three key components. That's for feature representation, for affinity estimation, and for optimization for association. Okay. So multiple target tracking is very challenging problem for several reasons. Okay, so one typical reason, which we'll show later, is the complex method design. Basically, we need to put all the components together, try to optimize them for a global solution, which means the target trajectory. So this is typically inefficient learning process because we usually learn each component separately, and it's hard to jointly learn all of them. There are other challenging parts. So one is that typically the current model, the lack of high order discriminative clues, so makes it harder to deal with cluttered scenarios like this. So in this work, we kind of jointly solve all this problem. So we proposed an end-to-end framework named FAMNet. So given image sequence and the candidate detections, so we will first send them to the feature subnet. So then we get some kind of features, and then we send the features into another subnet named Affinity subnet, which will give us the affinity tensor. So tensor means we have a high order kind of trajectory tracklist. Okay. And this tensor are sent into MDA subnet, which will produce the between frame association results. And then we pass this into target management to produce the final results. So during training, so once we have the ground truth assignment, we just design a kind of a typical loss function and then use backpropagation to jointly optimize the MDA subnet, the affinity subnet, and the feature subnet. So this way we can train the whole system end to end. Okay. So this slide shows the feature and affinity subnet. So the feature subnet is kind of very straightforward. It's just a SIMIS-like network. For the affinity subnet, we essentially concatenate features from three 3 consecutive frames by putting them together. So we implicitly capture the dynamics, and we also use mask attention for kind of prediction. So for association, we use the rank 1 tensor approximation framework, which captures high order information. So traditional solution is through rank 1 tensor power iteration. So in this paper, our main contribution is that we put this tensor power iteration, we make them differentiable. Therefore, we can pass the gradient through from the annotation all the way to each component. So this slide shows the running of our tracking system. It's just an example. So it shows how we deal with normal target and also target exits and the entrance. And you can also see sometimes we use single orbit tracking to improve the performance. Yeah. So we tested our method on a few popular benchmarks, including MOT15, MOT17, and the UA DataTrack and the KT dataset. So most of the time we will place either on the top or the second best. And we also provide ablation study in the paper, so details can be found in the paper. Okay. So in summary, we propose the end-to-end multiple target tracking system. We jointly optimize the feature learning and affinity learning and multidimensional assignment. So if you're interested, please stop by our poster at number 21. Thank you for your time.
All right, the third paper is titled as Learning Discriminative Model Prediction for Tracking.
Okay, so let's do some more tracking. Good afternoon, everyone. I'm Goutam Bhat. I will present our work, Learning Discriminative Model Prediction for Tracking. This is a joint work with Martin Danelljan, Luke Van Gool, and Radu Timofte. So generic tracking is the problem of tracking arbitrary objects in a video. You mark the target with a box, and the tracker should follow it for the rest of the sequence. So how is this done? Here is the standard tracking pipeline. The training frame is first passed through a feature extractor. Next, we learn a classifier online which can robustly distinguish the target object from the background. The classifier is then applied on the test frames to get a score map, the peak of which gives us the new target location. Ideally, we want the online learner to provide us with a robust model in order to avoid tracking failures. This is, however, tricky if we also want to learn feature representations end-to-end, as the gradients need to be backpropagated through the online learner in this case. This is feasible only if the online learner is differentiable and fast. This poses significant challenges on the design of the online learner. As a result, the most popular end-to-end tracking approach, the Siamese networks, do not use any online learner, using the features from the target drop as the model instead. This is then correlated with the test frame features dropped in the score map. This is obviously differentiable and fast. However, is the model robust? To find out, let's consider the scenario where there is a distractor object in the scene. We visualize the scores output by a state-of-the-art Siamese tracker, CMRPN++. Here, we can see that the model struggles to distinguish between the two dogs, even though the distractor dog was present in the training frame. This is because the Siamese model only uses the target crop, discarding the useful background information. Thus, in this work, we propose an alternate end-to-end tracking architecture which can learn robust models by integrating background information. Our network takes a set of training images and extract features. These are then passed to an initializer module which predicts an initial model in a Siamese framework. Next, we use an optimizer to refine this initial model iteratively by also integrating the background information. The output is the final model which you use to track the target. Let's look at the model optimizer in more detail. Our model optimizer is derived from the following discriminative learning laws. Here, R is a residual function which computes the error between the tracker prediction and the ground truth at every spatial location, and X is the training sample. So for end-to-end learning to be feasible, the key challenge is how to minimize this loss fast, using as few iterations as possible. We achieve this by using a steepest descent-based methodology wherein we compute the optimal step length at every iteration using Gauss-Newton approximation. This, in combination with the model initializer, allows us to get a fairly robust model in as few as 5 iterations. Our network is trained on video datasets. From a video sequence, we sample 3 frames as a training set and 3 frames as a test set. These are then passed through the network to get the scores for the test frames. We train the feature extractor, the model initializer, as well as the optimizer parameters end-to-end by minimizing the prediction error. Note that our framework also allows us to meta-learn the parameters of the lots itself. We study the impact of the model optimizer by comparing it with Siamese-like baseline with no optimizer. The result shows that the optimizer provides around 5% improvement in tracking performance. We also study the impact of end-to-end learning by comparing with a variant of our approach with no backbone fine-tuning. The results show that end-to-end learning provides a decent improvement. Next, we compare our approach with the state-of-the-art approaches on VOT18 and Lasso dataset. On both datasets, our tracker obtains the best results, outperforming the recent methods by a significant margin. Further, our approach operates at over 40 frames per second. Here, we show the scores output by our model on a few example videos. We can see that our model is fairly good at handling distractor objects. Our complete code and training models are available at the following link. Visit us at poster number 22 for more details. Thank you.
Right. Okay, yeah, before starting the question, so please do not ask the question for other groups' paper. So because we are going to flush the questions anyway after the presenting 3 papers, presenting all the papers in the group, so we cannot recover the old questions. So you please ask question for the current group of the papers. Okay. So one of the questions we have to ask is maybe there is a very simple question for paper number 21, FAMNet. So does the training data need to have the target and as well as the affinity annotations? So the training data has the annotation for the target and the association both.
The training data has a
Target information, target location, and association.
Oh, the training data has a target. Yeah, the training data has a full ground truth, the results.
Full ground truth for the association too.
Yeah.
Okay. Also, I have the question. So how do you handle the variable number of targets in the network? So network should be able to accept the variable number of the targets.
Yeah, that one to handle the kind of occlusion or missing object, we use essentially some dummy target. Kind of some virtual one, so that's actually in the rank 1 tensor decomposition framework. It's already in that framework.
Okay.
Okay, thank you.
Is there any question from the floor? Okay, let me select one of the questions that we have. Before that, so one question is. Actually, so for paper the 22, the question is what is the most important difference between DIMP and ATOM? They both use the GradNet 18 backbone. So can you answer the question?
So the biggest difference is in the online learning approach. So in DIMP, we have a much lighter online learner, so which allows you to fine-tune the backbone ResNet 18. So if you use the same backbone, like without any fine-tuning, then the results with DIMP are a bit worse. But like the optimization is faster, and with backbone fine-tuning, then the results are better, while the tracker is also faster.
All right. Any other question from the floor? Do we have just? All right. I think time is up. So let's thank the speakers and let's move on to the next group. Thank you.
So the next paper is DynamoNet, Dynamic Action and Motion Network.
Hi guys, it's audible, right? Yeah. So I'm Vivek. I'm presenting on behalf of Ali. He couldn't make it. So I'm a graduate student at KIT and also research affiliate at MIT and Harvard. This work is done with Luke and Rainer. So as the title says that we are trying to learn action recognition for sample-specific samples for dynamic motion representation. And this we achieve by predicting future frames and also recognizing the action and learning motion representation. This work builds on top of learning some state-of-the-art methods, and we try to avoid using optical flow map, and which we learn in the model directly by predicting future frames. So this is the method in which, we are trying to learn the motion representation in the model by predicting future frames and also jointly learning the action classification and also predicting future frames. So this is a self-supervised method since we predict the future frames on the fly by only seeing the short-term future samples. This is the whole pipeline. What we are showing in this pipeline is that basically you dump a bunch of clips and you generate the dynamic motion filters. And once you have generated the dynamic motion filters, which are convolved with the input samples, and you predict the future. And the future samples are, when they're predicted, they are basically minimized with respect to not the same time, but time and time plus one, using a Huber loss. And when I say that Huber loss, basically when you're trying to predict the future, so like you compare t and t plus 1, such that t plus 1 is compared with t plus 2, t plus 2 compared with t plus 3, and this way you can basically learn the motion representation by predicting the future frames, and that's what we show in this diagram. Basically, when you learn these filters, so these filters are built on some spatial transformer networks or dynamic filter networks, and which are currently very popular for learning the representation. And once you have learned this representation, what we have on top is a fully connected layer, which kind of takes all the information from all the filters learned, and then which is concatenated with the fully connected layer of the prior model. And then you also do action classification. So that is like action classification plus motion representation. And we hope that in this way, we learn some motion representation, and that has been hyperparameterized by alpha and beta, with which we govern how much flow information we should learn, and also what classification should be done. And we found that it works relatively well, and I will just switch to that and show that it works in the next slides. So in this, like what we are trying to show is that there's a self-supervised training, like lots of people are, it's very popular these days. So what we do is that we have no classification, but we use YouTube 8M dataset with 500,000 samples, and we just do future frame prediction. Once our model was fine-tuned on that, we basically use UCA for HMDB datasets, and we fine-tune those models with a fully supervised setup, and try to show that model learned in this way, it can actually effectively improve the performance of the self-supervised methods also, using the same setup of 3 splits of each of these data set and giving the average score of accuracy. And on the left, what you see is that we have results for kinetics 400, and on the right, you see the results for UCF and HMDB51. And certainly you can see that once you go to higher frame rate, as if like when you are trying to encode 16 frames or 32 frames or 64 frames, the predictions increases, and which we do expect because we have learned some nice motion representation, and that's effective. And just for qualitative evaluation, what we show is the last frame and the future frame predicted, which is like one future frame, and we show that the difference between the two predictions. And we found some motion representation, not sure if it is visible or not, but there is some motion information. We also tried to compare the optical flow and the predictions. You could see the difference of 2 frames. And you're welcome to attend my poster. Poster number is 23. Okay, thanks.
So the next paper is SlowFast networks for video recognition.
Hi everyone, so this is joint work with Haoqi, Jitendra and Kaimin. So the goal of this work is recognition in video, where the spatial semantics often evolve slowly. For example, a person is always in the person class, no matter if she's standing or turning. The motion being performed, on the other hand, can be much faster. So for example, can you recognize hand clapping of the person on the right? Indeed, this is much easier when we have fast frame rate. So our work is also in part inspired by neuroscience. So please have a look at the following video from an experiment around 40 years ago. So isn't it amazing what our brain is able to do with just motion information? A few dots that move in a certain way. So what do we know about the brain? The brain has two pathways. One is the ventral stream, which is responsible for object recognition, face recognition, and it originates with parvo cells. Parvo cells are the majority of cells in the retina, and they are having a slow conduction rate, which means they can only slowly propagate information of color or semantics. There is also a dorsal stream, which is responsible, for example, for motion recognition. And the dorsal stream originates with magno cells, which have fast conduction rate, which means they can quickly propagate information. However, there are only around 20, from all the cells, they are only around 20%, so the minority. There are also lateral connections between the two pathways. So the basic idea of slow-fast networks is to use two pathways. One is a slow pathway that operates at low frame rate to capture semantics, and a fast pathway that operates at high frame rate to capture motion information. The slow pathway is a residual network, a 3D ResNet applied to low frame rate with low temporal resolution T. The fast pathway is applied to high frame rate video and therefore has high temporal resolution, alpha times higher temporal resolution. However, it is made very lightweight because it uses beta times less channels, so it has overall just like 20% of the computational cost. This is in proportion to the parvo-magno ratio. There are lateral connections that fuse the two pathways. In our ablation studies, we compare several slow-only architectures with different computational complexity shown in the horizontal axis of this plot to their fast or slow-fast counterpart shown by the green arrows here. So in the vertical dimension, we see that the accuracy increases by adding the fast pathway, but just a small increase in computational cost because the fast pathway is very lightweight, even if the slow pathway already uses high frame rate. So the model performs state-of-the-art for action detection and classification. On the next slide, we show the class-level performance gain of the model when using slow-fast over the slow-only counterpart in blue. And we see by the green bars that there are increases for highly dynamic actions, such as running, jogging, hand clapping, and so on. Our detector is similar to faster RCNN applied to video. So what you see here in the video are by green boxes our detections with the confidences on the top, and the red boxes show ground truth with the annotations on the bottom of the people. The video illustrates the difficulty of this task, as multiple actions have to be recognized in both space and time. So the model performs state-of-the-art compared to previous works, but we also participated in this year's ActivityNet challenge in the AVA track, where we got a 13 MAB boost over the previous year's challenge winner. And also the top 3 ranked teams all used slow-fast networks as their backbone, which shows that the method is generally well adoptable by the community. So in conclusion, this talk has presented slow-fast networks which contrast the speed across the temporal axis. It performs state-of-the-art for detection and classification, and also shares some interesting relations to neuroscience. Our code is available in PyTorch at the following link, and we hope that this slow-fast model can foster further research in video recognition. Thank you very much.
Next paper is Generative Multi-View Human Action Recognition.
Hello everyone, this is Chen Mingding. Today I'm glad to be here to share with you our work on generative multi-view human action recognition. This work was jointly done with my previous colleague and advisor. The task of multi-view action recognition is to benefit from the action sequences from different sensors like RGB sensors and depth sensors to enhance, to improve the action prediction performance. Since the data are captured from different sensors, so we will have several challenges. One is heterogeneous feature domains. So you know the RGB data and depth sensor data, they are very different. Another thing is during the data collections, we may have some challenges like the devices issues and some occlusions. We will have some missing data during the data collection. And we also have the inconsistent view-specific predictions. That means if we build learning models for each view-specific action sequences, we will get different results. So in this sense, we propose 3 modules to handle this, and we will illustrate one by one. First is the view-specific encoder. So the idea is we want the view-specific encoder to transform the original action sequences to a latent space. And in the latent space, we want the same action data to be close with each other and to achieve more discriminative informations. And we explore the label information and the trip loss to align the data from different views in the latent space and to be more discriminative. Considering the missing data in the training stage, we explore the cross-view adversarial generations. So the idea is we want to generate the missing data in each view conditional on other views. So here we only show 2 view cases, so we have 2 generators, G1 and G2 is conditional gain. So in this sense, with more data, we can improve the view-specific encoder learning to enhance the cross-view representation. The last module is we call the view correlation discovery network. The idea is we want to fuse the knowledge from different views. And as we mentioned, if we build view-specific classifiers, prediction will be inconsistent. So what we do is different from the previous fusion strategies. We will show the benefit. What we do is we use initial prediction from each view-specific projections and to learn a cross-view discovery matrix, then input to our view correlation discovery network, we call VCDN modules, to do the final prediction. So here we show 3 different laws for the 3 classifiers. C1 and C2 are the same, and the VCDN is different. So we will do the ablation study to see why VCDN helps. And all 3 modules are trained together in an end-to-end manner. And we will show the evaluation on the multi-view action recognition tasks, and we also will evaluate different modules. So here is the result. We evaluate on 3 data set, multi-view action recognition data set. And we also do some pre-processing to remove some data from each view to build the missing data challenges. Here we compare with several other state-of-the-art multi-view action recognition method, and from the result you will see the better performance. Here is we did ablation study by removing the generative models to see if the generative models helps. So from the curves we can see the solid curves achieve better performance than the dot curves. That means the generative models help. And we also did everything study for the VCDN module, since we use a different strategy to fuse the knowledge. And we compare with several fusion strategies like feature and label concatenations and label average fusion or label weighted fusions. And we even compared with the regular neural network like SoftMax, the classifier. So here we show the result. You can see the VCDN modules can beat other comparisons. That means that shows effectiveness. To sum up, we propose 3 modules in a unified model to handle the 3 challenges in multi-view action recognitions, and the experiment shows better performance. And welcome to our poster. Actually, the poster is in 25. Yes, thanks.
So we will start the questions now. If you have any questions from the floor, just approach a microphone and try to catch our attention because we don't see much from here. So we have already a couple of questions from the Slido system for paper 23, the first one. Would your approach be able to predict more than just the next frame? And if so, up to what length in the future?
So in this work, what we have tried is only predicting the next future frame, like predicting one frame at a time. But I think it should be applicable to more future frames, but we haven't tried it.
Okay. I have also a question. Are you able to handle any frame rate, or do you need to train it separately for different frame rates? Like you show several results with different frame rates.
So no, it's the same thing. It's just that like what we have is we predicted 16 filters. So if you have more, then we have predicted 32 filters or 64 filters. It just depends how much you want, but it has a computational cost. Like for academicians, it's not the same, but yeah, one can do it.
Okay, thank you.
You're welcome.
So we have also questions for paper 24. What can you tell us about the transformations you use for test time augmentation?
So for test time augmentation, we don't use, in our basic results, we don't use any augmentation for AVA. So we do fully convolutional testing without any flipping or multiscale testing. We also don't use any multiscale testing for the kinetics results or for the classification results. So this is a common testing procedure that has been used in previous works. Basically, it is temporal clipping across the temporal axis with 10 different clips. And spatially, it's left, center, right cropping.
And there is a second question from the system. Does it perform well on datasets where optical flow is critical, such as HMDB51?
Yeah, actually, we trained it on UCF101, which is pretty similar to HMDB by fine-tuning from kinetics, and it says like 97.5. So it works just as two-stream networks, I think.
Okay, so for paper, we have another question for this paper. How are frames sampled temporally? Is there a sweet spot in the ratio between the slow and the fast frames?
So yeah, so we have an ablation in the paper. We have like extreme cases where we just use one frame, for example, for the slow pathway, and 16 times the number of frames in the fast pathway. But generally, there is a better trade-off if the slow pathway has less frames and the fast pathway has more frames in terms of accuracy versus complexity. However, the accuracy goes always up if you use more frames in the slow pathway as well, which is the heavy pathway.
Okay. Thank you. That's, we have no more time for questions. Thanks the speaker again.
Right, next paper is paper number 26, multi-agent reinforcement learning-based frame sampling for effective untrimmed video recognition.
Hello everyone, I'm Wen Hao, a master student at the Chinese Academy of Sciences. This work was done with Danelljan, Xiao, Shifeng, and Shilei during my internship at Baidu. I really appreciate this opportunity to do the presentation. At the beginning of my internship, my mentor asked me how to improve the accuracy of recognition for untrained videos, since there are a huge amount of videos on Baidu Cloud. In my opinion, it's intuitive to think about these questions from two dimensions, basic recognition model and the sampling method. For basic recognition model, great progress has been made. I personally divide it into two aspects, end-to-end method and the two-stage method. You know, the current state-of-the-art model are the variants of 3D CNN, which may be hard to reproduce or improve with limited computing resources in a short time. So I try to focus on sampling method, which is paid limited attention relative to basic model. In fact, for untrained videos, not all the frames consistently correspond to the ground truth label, and picking out the informative frames can be an effective method. It's intuitive for humans to pick out informative frames as follows. First, we observe several frames, then we infer where to check next time, until we find out satisfying frames round by round. Motivated by this, we proposed our multi-agent reinforcement learning-based sampler. Each of the agents is responsible for selecting one informative frame. At each 10th step, each agent relies on contact information to take action for adjusting sampling location. When all that stop, we can get a video level prediction. Our framework is composed of a contact-aware observation network for capturing environment state, a policy network for estimating probabilistic distribution over action space, and a classification network for video level prediction. Each of the agents interacts with the environment by taking action to adjust the sampling locations at each 10th step. The contact-aware observation network is designed to allow the contact information communication among nearby agents. So the overall objective of our framework contains two parts. For multi-agent reinforcement learning objective, the reward function reflects how good the action was taken by the agent. Following reinforce, we use Monte Carlo sampling to get a policy gradient. We also follow the practice of using entropy of policy to increase the ability to explore. For classification objective, we use cross-entropy loss. Finally, we minimize the hybrid loss. Here we examine our framework with different backbones on ActivityNet datasets using the RGB frames. For each backbone, we use 3 baselines: random sampling, uniform sampling, and using all frames. And our method achieves the best performance regardless of shallower or deeper baseline models. In the figure, we make comparison under the scenario of observing the same number of frames, and the results demonstrate the effectiveness of our method. We also compared our method with the other state-of-the-art models on several datasets. Our sampling method can be applied to existing on-chain video recognition models to improve their performance. Then we visualize some examples of selected frames with different strategies. From top to bottom are uniformly sampling, our method without contact-aware observation network, and the last row is our method. We perform ablation study on ActivityNet dataset for different numbers of agents. Then we try to explore the impact of contact range in contact-aware observation network. The contact-aware observation network improves the non-contact model with clear margins. We also found the learned policy network can still be effective when it's transferred directly to other datasets or other classification networks. In short, we proposed an intuitive and simple idea for on-chain video recognition, and I think there will be more better approaches in the future. Thank you for your attention, and welcome to our poster for any further questions.
Okay, next is paper number 27, SC Sampler, sampling salient clips for videos for efficient action recognition.
Hello, my name is Bruno, and I'm going to present an SC Sampler, our take on solving a problem of long untrimmed videos where only few segments are actually salient and meaningful for action recognition. So, traditional approaches mostly take 3D CNNs applied on either all or some clips of the video, and then they pull the information from the entire video. This becomes computationally costly because the classifiers are very heavy, but also it can actually decrease the performance given the number of irrelevant samples. We introduce an SC sampler, which is a simple lightweight model which can be applied to every clip of the video, and using that filter to apply heavy clip classifier to only really relevant clips. The way to make it lightweight is to use features which can actually be either extracted without decoding or very lightweight to process through typical FAMNet. So One such feature is actually audio, which is stored separately from the video, and it's very easy to process. We can fit an hour-long video in a single batch by simply transforming it to a ML spectrogram and passing through VGG, and to obtain the sampling score at the end through either a fully connected layer or predictions. Similarly, for visual SE sampler, we can also look at the compressed video features. So most codec actually rely on some form of compression, meaning they store the RGB frames only ever so often, while in the meantime they store low-dimensional either motion displacement or RGB residual for subsequent frames. These frames can be read very quickly, and we can pass them through simple networks, ResNet 10 or 18s in our case, which makes it much more computationally, much easier computationally, and we can simply average or pull the results from all three of them separately. Again, we can process hours of video on a single GPU in a batch or two. Note that there are actually no labels for saliency. So there are two ways we found that work in training these networks. First one is to train it as an actual classifier, so using a simple cross-entropy loss on the target classes, and then pulling the predictions to use as a saliency score. This worked really well for a visual SE sampler, so for compressed features. And then we've also experimented with a ranking loss. We can fine-tune the networks to learn according to the classification model by creating a pseudo ground truth by using the heavy clip classifier and using the confidence score with respect to the true label as a label, and then train a sampler to rank more confident samples higher than the low confidence samples. This approach worked for audio, which has less signal information than visual stream. We evaluate all of these design choices on a small subset of sports 1 million. And we benchmark against the most common sampling techniques, which are random, uniform, and using all non-overlapping clips. We see that both audio, visual, and joined SE sampler work significantly better and give significant improvements in accuracy over this artificial dataset with a large speed up on 32 GPUs. And furthermore, on the large-scale dataset, we see about 7% improvement over what is already a state-of-the-art method, and reduce the cost by 15 times without retraining the model whatsoever. And similarly, even on kinetics, which in principle doesn't really need temporal information, we see very marginal but consistent improvements over all methods with barely any reduction in computational cost. Thank you very much. So our project page is up with the scores and more information. And this was done in collaboration with Facebook AI, Du, and Lorenzo. Thank you very much.
Okay. Next paper is weekly supervised energy-based learning for action segmentation.
Hello everyone, I'm Junli. I'm from Oregon State University. In this paper, we address action segmentation under weak supervision. The following is our problem statement. Given a video, our goal is to label every frame with an action class. We focus on a weakly supervised setting, where training video do not provide ground truth labels for all frames, as shown in this example. But instead, in training, we are only given the ground truth temporal ordering of actions, which is more challenging than the common fully supervised setting. The key challenge here is that there are multiple valid action segmentations that satisfy the ground truth ordering of actions. For example, in this figure, we show that different start and ends of video actions, but only one of them is correct. Here is an overview of our approach. We use the GRU for labeling every video frame. Our main contributions are aimed at a weakly supervised training of the GRU. The key idea here is to use an energy-based loss for training that will efficiently account for both legal and illegal action segmentations of training videos. So our first contribution is the formulation of a new laws in terms of cumulative score for all legal and illegal segmentations. Our second contribution is an efficient method for computing these cumulative scores. Our training begins by using the Viterbi algorithm to find an initial optimal legal action segmentation that satisfies the ground truth temporal action ordering. For robustness, we allow the initial action boundaries to move in a local temporal window. Finally, every path in the segmentation graph corresponds to either a legal or illegal action segmentation. In the segmentation graph, we define the edge weights as the summation of GRU's negative log softmax score over the frames between two cuts. The energy of a path is the summation of edge weights along the path. We propose our energy-based laws that address both legal and illegal paths with an auxiliary log-edge function. Therefore, our key contribution is to use the log-edge function for efficient computation of the total energy. In particular, the log-edge function computes the total energy in a recursive manner. We evaluate our model on two tasks, action segmentation and action alignment. For action segmentation, we are only given a test video for frame labeling. For action alignment, we are given both a test video and its ground truth ordering of actions for frame labeling. Here are our results. Our experiments on action segmentation demonstrate that we outperform the state of the art on the breakfast and Hollywood extended datasets. Also, our performance on action alignment tasks is superior to the state of the art on the same datasets. In this slide, we illustrate our performance on action segmentation task. We use a sample test video from the breakfast dataset. The video is about a person who is making milk. The action sequence consists of 4 actions shown in different colors. By temporarily aligning our model results and the ground truth labels along with the video, we clearly show that our model makes a good prediction and may miss the true start and end of some actions for just a few frames. But in general, it can successfully detect the correct temporal action ordering and makes a good frame-wise action labeling. Thanks for your attention. You are welcome to visit our poster number 28 this afternoon.
All right, there are several questions in Slido system. The first question is, how do, for paper number 26, how do multi-agent cooperate with each other? It says the agent works separately.
It's a good question. We use simply concat the feature of nearby agents to access information.
I see. So another question is, how do you make sure that the agent do not end up sampling a single frame?
Sorry?
So how do you make sure that the agent do not end up sampling solely, for example, the beginning of the clip?
Okay. I think it's possible, and we may try to use adaptive step in our future work. Yeah.
I see. One question for any question over there? Yeah.
Hi. I have a question for first two speakers. Ideally, if the agent or if the network can sample the action needs of the frames, then could you ever measure how many the ratio between the action and non-actions?
So yeah, for sure. We have actually done a little bit of ablations in our supplementary material. It really depends on the data set. So for instance, for Sports 1 million, we found that only about a fifth of a video contains relevant information. This is with respect to the action classifier. However, for kinetics, we found that pretty much all of the segments are equally distributed. So, yeah.
Right, does it answer your question?
Actually, I asked two speakers. Yeah. The first one, the second speakers.
The first paper?
Yeah, first paper too.
Okay, sorry.
So could you quantitatively measure the action needs of the sampled frames?
Okay. I think I may think about it. If you want more details, we can discuss in the poster. Okay.
Okay. Is there any other question from the floor? Yeah. Please.
I have a question about the third paper. Just during the inference, I just want to know if your decoding is using the transcripts of the training set for picking the best transcript?
Yes, we enumerate all the transcripts appearing in the training dataset.
So your model is not learning the transcripts, right?
No, actually.
And what if there is no shared transcript between the test set and the test split and the training split?
We assume that they share some common knowledge, and we assume that it's a prior.
Okay, thanks.
All right, thank you so much. Let's thank speaker again.
So the next three speakers, can you come up, please? So the next paper is what would you expect anticipating egocentric actions with rolling unrolling LSTMs and modality attention.
Good afternoon. My name is Antonino Furnari. I'm from the University of Catania, Italy, and the work I'm presenting today is co-authored with Giovanni Maria Farinella. Humans have remarkable abilities to anticipate what is going to happen in the near future. We use these abilities on a daily basis to deal with a continuously changing environment and to interact with each other. Anticipation abilities are fundamental also for machines, especially when they are designed as innate to humans. For instance, consider a worker equipped with a wearable device. It would be ideal if such a wearable assistant could anticipate the user's next moves and give an alert whenever a potentially dangerous action is about to be performed. In this paper, we consider the problem of egocentric action anticipation. That is, given the observation of a video segment, predict the action happening in a given number of seconds, for instance, in 1 second. We argue that this is best done in 2 stages. In the encoding stage, we observe the video and produce a semantic representation, which may include what actions have been performed and what objects are present in the scene. In the inference stage, we use this representation to guess what is the next likely action to be performed. We note that these 2 tasks are performed jointly by past methods and propose to disentangle them by using 2 separate LSTMs. We take inspiration from sequence-to-sequence models. These models comprise an encoder, which analyzes the words of the input sentence, and a decoder, which generates the words of the output sentence in an autoregressive fashion. We adapt this architecture by replacing input words with high-level representations of frames obtained by using a CNN. The decoder iterates over the last representation for a number of time steps proportional to the anticipation time. The decoder is also attached to each encoding step in order to continuously predict actions in multiple anticipation times. We term the encoder and decoder rolling and unrolling LSTMs. To encourage the rolling LSTM to focus only on encoding, we propose a sequence completion pre-training technique. During pre-training, the unrolling LSTM looks at future representations to make predictions. This allows the rolling LSTM to concentrate on encoding rather than anticipation. After pre-training, the network is fine-tuned for action anticipation. Following previous literature, our model processes the video according to different modalities. In particular, we consider RGB frames, optical flows, and object-based features obtained by running a faster CNN on the input frames. We train an instance of our rolling architecture on each modality to obtain modality-specific action scores. We argue that in the case of action anticipation, the relative importance of each modality might depend on the observed sample. Hence, we propose a modality attention mechanism which computes late fusion weights in an adaptive fashion. The internal representations of modality-specific rolling LSTMs are fed to a multi-layer perceptron which outputs fusion weights. These weights are hence used to compute a weighted average of the modality-specific action scores, and the whole model is fine-tuned end-to-end using backpropagation. We evaluate our method on two benchmark datasets of egocentric videos, Epic Kitchens and eGTA Gates Plus, on which we obtain state-of-the-art results on the tasks of action anticipation and early action recognition. This amounts to improvements of up to plus 5% on Epic Kitchens. Ablation on Epic Kitchens shows that the proposed rolling LSTM improve over a single LSTM baseline. Modality attention outperforms standard late fusion, and not performing sequence completion pre-training results in a performance drop. Our model achieved the highest top 1 and top 5 action accuracy on both S1 and S2 in the Epic Kitchens egocentric action anticipation challenge. Thanks to the processing of RGB frames, optical flow, and objects, as shown in the bottom right corner, our model can effectively anticipate actions, including verbs and nouns, even in complex scenes with many ongoing activities. Moreover, the method can predict actions and multiple anticipation times, ranging from 2 seconds down to 0.25 seconds. By observing more frames and detecting objects, our approach can refine predictions in a continuous fashion. We released the code of our method on GitHub to encourage research on this challenging problem. The code can also be used as a basis to participate in the upcoming Epic Kitchens egocentric action anticipation challenge. Please come to poster number 29 for more details and discussion, and thank you for your attention.
The next paper is PI, a large-scale dataset and models for pedestrian intention estimation and trajectory prediction.
Hello everyone, my name is Amir and I'm going to present a paper on pedestrian intention estimation. Pedestrian action prediction is a fundamental component in autonomous driving systems. It helps avoid accidents and potentially can improve traffic flow. To predict pedestrians' actions, it is necessary to understand the intention. What do we mean by intention? Assume several pedestrians. We are making an observation of their appearances, the surrounding context, their motions, and also we take into consideration the vehicle sensor information based on which we make a prediction of their future trajectories or their actions. In this case also, of course, we are interested to know whether they are going to cross in front of the vehicle or not. Given this scenario, we can consider intention as an intermediate step between observation and prediction. In fact, it reflects the underlying motives of people to perform an action. For example, if somebody has no intention of crossing, perhaps waiting for a bus, obviously is not going to cross. And if somebody has an intention of crossing, depending on the traffic flow, the state of the signals may or may not attempt to cross the street. Collecting intention data is challenging because, of course, we need to directly interview people. The alternative would be that we make some sort of a judgment on their behavior and on their intention. Judgment, however, can be subjective if we don't use large enough number of people. To address these challenges, we are proposing pedestrian intention estimation, or PI dataset. This dataset contains more than 6 hours of footage collected in downtown Toronto, Canada, and is recorded on roads with different structure, traffic densities, and crowd of people. Using this dataset, we conducted a large-scale human experiment. For that, we selected 1,842 pedestrian samples. We extracted 3-second clips for each sample, and we showed these clips to the participants. Each participant was shown a question, does this pedestrian want to cross? And they had to specify how confident they are in the intention of crossing. Overall, we collected 5 responses per clip from in-lab participants, 10 from Amazon Turk, And in total, we collected more than 27,000 responses from 700 subjects. Now I'm going to show you a sample of how the experiment looks like in practice. So we start by showing the question to the participant. We ask them, does this person want to cross? Next, we show the clip, and we identify the pedestrian we are interested in. We play the clip, and at the end, we freeze it again, and again, identify the pedestrian that we are interested. The question is again displayed to the participant, and they have to specify their confidence. Here are the responses from the average responses from the people. The green one shows the in-lab responses, and the red dot shows the average responses of the Amazon Talk workers. As you can see that there is a general agreement among people when they are judging the intention of pedestrians. Our dataset also comes with other annotations in addition to intention. It also has the pedestrian bounding boxes, the behavioral tags, the bounding boxes for traffic elements, the vehicles, the crossing lines, the road boundaries, and also we have all the information read from sensor data on the sensors on the vehicle. So the proposed model for this data set is a 3-module model which has an encoder-decoder architecture. The trajectory prediction module on its own and using only bounding box information achieves the state-of-the-art performance on the proposed data set and also on the JAD data set, which is another behavior understanding data set. Our intention estimation module is a baseline model which uses the appearance of the pedestrians, the surrounding context, and also take into account the motion of the pedestrians in order to estimate their intention. And last but not least is the module that predicts the future speed of the vehicle given the current sensor readings. Putting all of these modules together, you can see that gradually adding this new information to the trajectory estimation stream, it can potentially improve the results. Showing you an example in practice, we can see 2 sequences here. We start by ground truth bounding boxes, prediction only using the location information, location and the speed of the vehicle, location and intention of people, and putting everything together, which the best result is achievable. In conclusion, we proposed a new large-scale data set for pedestrian intention estimation. We conducted a large-scale human experiment to establish human reference data, and we proposed models for onboard trajectory and intention estimation. And we also showed that intention does matter and it can potentially improve the results. Thank you for your attention, and please come see us at poster number 30.
The next paper is STGAT, Modeling Spatial-Temporal Interactions for Human Trajectory Prediction.
Hello everyone. It's a great pleasure to present our work as STGAT, Modeling Spatial-Temporal Interactions for Human Trajectory Prediction. We are from the Institute of Computing Technology, Chinese Academy of Science. Trajectory prediction is defined as predicting the future trajectory of a pedestrian given the observed motion trajectory. It has many potential applications, including delivery robots, crowd motion analysis, and abnormal detection. But it's a particularly challenging problem. Among other challenges that exist, the key one is how to model the human-human interactions. As we work in crowded spaces, we are socially aware of our neighbors and implicitly assign different importance to them. In this work, we mainly focus on how to model the human-human interactions. These figures demonstrate how baseline methods model the interactions. All of these methods primarily consider location proximity when assigning weights to neighbors, but there are also many other influences, for instance, velocity, acceleration, and heading. In contrast, our methods use an attention mechanism to assign weights by motion status. Inspired by the recent success in graph neural networks, we treat pedestrians in the crowded scenes as nodes on the graph at each time step. We use graph attention network to model their interactions, as it allows for aggregating information from neighbors by assigning different importance to different nodes. We also noticed that when we walk, we need to consider others' historical moment to determine our current motion behavior. So, besides the spatial interactions at the same time step, we also model the temporal continuity of interactions. Now, I will introduce our model. First, we use one LSTM for each pedestrian to get the motion state as in many previous works. At each time step, the motion state of each pedestrian is represented by the hidden state of the LSTM cell. And we use graph attention network to aggregate the motion state of each pedestrian to model the spatial interactions. And also, another LSTM is adopted to model the temporal continuity of interactions. At the last observation time step, the hidden state of two types of LSTMs are concatenated and sent to decoder module for generating future trajectories. For evaluation, we observe 8 time steps of the history and predict the next 8 and 12 time steps. We use the standard evaluation metrics ADE and FDE to measure the performance of the algorithm. At the far right is our model. It shows that our approach outperforms the best baseline model with around 20% improvement in accuracy on average. Here are the best prediction results of our model and best baseline model in 2 cases. The second line is our model. The red is the observed trajectory, the blue is ground truth, and the yellow is the model prediction. Our models performs better as we generate trajectories closer to ground truth. We visualize the attention weights. Here are the results in 4 representative scenes. In these figures, the trajectory without circle are the target pedestrian. The radius of the circle is proportional to the attention weight. In this moment, in the top figure, when surroundings move towards the same direction, the pedestrians in front has more significant influence. In the left figure, the model assigns higher weights to pedestrians moving in opposite directions, even they are farther apart. In the 2 figures on the right, the model assigns higher weights to nearby pedestrians and nearly equal weights to pedestrians who are far from the target. Of course, there are also failings. The analysis of failings and other details of the model can be found in the paper or poster. To conclude, the graph attention network are more suitable for modeling human-human interactions, and consider the continuity of the interactions will improve the accuracy of the prediction. The code has been published. I'm very sorry for my poor English. If you are interested in our work or have any questions, please come to our poster. Thank you.
It's time for the Q&A session. If you have questions, please approach the microphones on the floor. So we have a first question from the Slido system for paper number 30. It's a question about the privacy of the detections. How do you actually deal with that in your data set?
Sorry, I didn't hear that.
A question about the privacy of pedestrians in your data set.
Privacy. Well, we are trying not to disclose the location information in detail, but we do have all the required permissions for it, so I don't know beyond that what I can say. We don't really specify exactly when and where it was located, but we have all the other information.
Okay, I have one more question. Yeah. Did you annotate just a single frame per video or multiple frames?
No, all the samples, they have a unique ID, so there's a temporal correspondence, and they are annotated across all the frames with 30 frames per second.
I see. So then do you have any statistics about the intention, the annotation with respect to the distance to the pedestrian?
So the way we selected the samples was based on the behavioral data, so the clips. So usually the point that people make crossing decisions is about 2 seconds to the vehicle. Mm-hmm. So we collected the sound. So in terms of timing, the clips are stopped at the point that there's 2 seconds left to the pedestrian we arrive. So all of them are consistent in that manner because that's when they make basically crossing decisions.
So I have a question for paper 29. So you say that you have, as far as I understood, 0.2 second future prediction. So what about more long-term prediction? Because it might not be fast enough for the person to change what he or she is doing.
Yeah, sure. So we consider this time horizon from 2 seconds up to 0.25, and we didn't investigate further. I'm not sure if the architecture might allow that, but that's, I mean, the general input-output pattern would allow to train the model, but I'm not sure what the result would be for a longer time horizon.
Okay, thank you. Any question from the audience? Yes?
This is a question for the STGAT paper. So use a graph neural network to aggregate the results from all the individual LSTMs for each human. Is there any restriction on the number of humans because you've got to construct a graph?
Your programs involve some implement details. I can't explain it here in few words, so please come to your poster. We can have a talk. Thank you.
Okay, so a quick question for paper 29. Using head-mounted hardware for video recording results in occluded hands, how would your system respond to such videos?
Sorry, what's the question again?
So if you record the videos from a head-mounted camera and the hands are occluded, how would your system respond to such videos?
So if the hands are not visible,
exactly.
Is that the question? Oh, well, so we are not explicitly processing hands or detecting them, so I guess it would work because the main input is the scene, the flow, and the objects which are there. So I would not, I don't expect any surprises.
Okay, let's thank the speakers again.
All right, the next paper is paper number 32, learning motion in feature space locally. The learning motion in feature space locally consistent deformable convolution neural network for fine-grained action detection.
Hello, I'm Mike from UIUC. I'm presenting our paper, Learning Motion in Feature Space. This is a joint work with Diraj, Raymond, Xinjun, Rogerio, and Min. So in this paper, we want to detect segments of fine-grained actions from a given video. Fine-grained actions are actions that are difficult to visually distinguish based on individual frames. Traditional approaches usually have two steps. The first one is to extract the spatial-temporal features, while the second one is to model the long temporal dependency. Spatial-temporal features usually use optical flow and multi-stream inference, which are usually expensive and noisy. Here we focus on the first step and propose to model the motion in feature space using changes in adaptive receptor fields in a single-stream network. Let's look at an example of fine-grained action, cutting lattice. Here are two input frames at time t-1 and time t. Notice that the arm is moving slightly. If we look at an activation location on the background region for each of the frames from a trained deformable convolution network, we can see that the adaptive receptor fields are nearly identical. However, if we look at an activation location on a moving region, the adaptive receptor fields are different. We visualize the magnitudes of such difference for on activation locations. As can be seen, the region with motions corresponds to higher difference. It motivates to model the motion using a difference of adaptive receptor fields. We first review the definition of deformable convolution. Here X is the input, W is the filter, and Y is the output. This is like a standard convolution except for the index inside X being deformed by the two dots. This is the deformation offset learned from other filters, HK. Here we have the default receptor field corresponding to an activation unit. Because of the deformation offset, the receptor field is deformed accordingly. We then define the adaptive receptor field at time t as ft, which is the collection of the indices inside X. We choose to model the temporal information, the notices R, as the difference between ft and ft-1, which essentially is delta t minus delta t-1. Notice that R is non-zero for deformable convolutions. However, directly modeling motion like this is not effective because there's no guarantee of local consistency. So what do we mean by local consistency? We can see that data to dots corresponds to XM, but there are many ways to decompose M. The problem happens when we move the activation unit to the next location. Since there are no enforcing of local consistency over the adaptive receptor fields, they can be freely assigned with any kinds of deformable offsets. Therefore, the overlapping regions can have many kinds of deformation vectors, making the motion field inconsistent. To solve this, we propose the locally consistent deformable convolution as follows. The difference here is that we restrict delta 2 dots nk with delta 1 dot n plus k with lower dimension. Here we have the same activation unit and adaptive receptive fields as in the previous slide. When we move the activation unit, LCDC enforces the local consistency over the adaptive receptive fields. Thanks to that, we can produce the consistent motion field. Now, putting everything together, we're given a short video snippets where the frames are VT. Each frame is fed into our network. The weights are shared for all frames. We use the outputs of the last layers for appearance information, while motion information is coming from multiple layers. They are then combined in the fusion motions to produce the spatial-temporal features. Such feature will be used in the long-temporal model. Here are our results on 50 Salas dataset. We compare multiple setups using spatial CNN features and our LCDC features. As can be seen, when LCDC is used with long-temporal models, the performance increases. We achieve the best performance using LCDC and EDTCN. In this paper, we model motion in feature space, and to do so effectively, we propose a locally consistent deformable convolution. Please come to our poster for more information. Thank you.
All right, next paper is the dual attention matching for audio-visual event localization.
Okay. Hello, everyone. I'm Yu Wu from Baidu Research and Railer, UTS. I'm glad to be here to present our paper, Dual Attention Matching for Audio-Visual Localization. The audio-visual localization includes two tasks. The first one is the cross-modality localization. The input is an audio sequence and a visual sequence. The target is to synchronize them. Given an audio query from other devices, it can be used to retrieve relevant clips in surveillance videos, which usually has no sounds recorded. And the second task is the supervised audio-visual event localization task. The input is the synchronized audio and synchronized visual signals. The output is the event category, including the background. Previous method on this task first divide the video sequence into short segments, and then they minimize distance at the segment level features. However, this method considers only segment level alignment and overlook the global co-occurrence in a long duration. So here comes our motivation. To better understand the event at a high level, we need to watch the whole sequence, and then we should check each shorter segment for localization. This is our method. Given an input audio, we first use pre-trained model to extract local features, and then we drop this background segment. On this event segment, we use a self-attention on it to get the global audio feature. On the other hand, we also have the visual input and visual local features. We want to use the global audio feature to check each local visual feature, so we just multiply them. The output is the event relevance prediction. Here we have the ground truth for each relevance, and 1 indicates they are relevant and 0 means they are not. Similarly, we have we also use the global feature from visual inputs to check each audio local audio features. This bidirectional prediction should be consistent. So this is the overview of our DEM module. Based on the DEM module, we build our pipeline to the first task, task 1. For example, we input the audio query to DEM to obtain a global representation. and then we check each visual candidates to predict a relevant score. So finally, we will output the continuous segment that has the maximum scores. For the second task, we propose to decouple it into two subtasks. That is, we first predict the event category and then differentiate the background from the event segments. So the final prediction equals event category plus the event relevance predictions. So here is our pipeline to task 2. Given both the audio and visual inputs, we first extract these local features. Here we use audio-guided attention to enhance the local features. And then we use self-attention to obtain a global feature. The next, we concatenate them to predict the event category. On the other hand, we also input this global and local feature to our DEM module, and DEM will output the event relevance score. So, and the final prediction is a combination. We validate our DEM on the AVE dataset, which contains about 4,000 videos and 28 categories. On task 1, our method outperforms the state of art by about 7 points on average. This proves the effectiveness of our DEM. On task 2, we also improve previous method by about 2 points. We also evaluate different sequence embedding functions, and we found self-attention outperforms the rest, such as STM and GRU. We also show some ablation studies and compare the cross-matching and self-matching. Cross-matching outperforms self-matching by about 16 points on task 1 and 0.3 on task 2. These are some qualitative results. Green indicates the correct matching, while the red means they are mismatched. The first one is matched, while the other two cases failed to identify the event boundary. Okay, thank you.
All right, next paper is uncertainty-aware audio-visual activity recognition using deep Bayesian variational inference.
Thank you. Hi, good afternoon. I'm Mahesh Subedar from Intel Labs. I'm presenting our work on uncertainty-aware multimodal Bayesian fusion framework. We demonstrate our results on audio-visual activity recognition, but this work can be extended to other multimodal applications. So first, the motivation. Audio and vision are complementary inputs, where some activities are easily detectable in one modality than the other. As shown in these examples, depending on the activity, single or multiple modalities can be reliable. There are also cases where out-of-distribution classes not seen during the training stage. Therefore, it is essential to model reliable uncertainty estimates for individual modalities to benefit from the multimodal fusion, especially in the case of real-world applications. So deterministic DNN models provide state-of-the-art classification results, but may fail in the case of noisy or out-of-distribution data, leading to overconfident decisions that could be erroneous. On the other hand, probabilistic Bayesian deep neural networks provide reliable uncertainty estimates. Hence, we are proposing a hybrid Bayesian DNN with stochastic variational inference to reliably estimate uncertainty associated with individual modalities for multimodal fusion. This is our model architecture. We use ResNet 101C3D for vision and VGGish architecture for audio modalities. We replace the final fully connected layer for both vision and audio DNN models with 3 fully connected variational layers, followed by the categorical distribution. During the prediction stage, we perform multiple Monte Carlo forward passes on the final variational layers by sampling the parameters from learned posteriors to measure uncertainty estimates. We calculate an accuracy versus uncertainty metric for individual modalities. An optimal threshold that maximizes AVO metric is used for multimodal fusion. The posterior distribution of the model parameters W is given by Bayes rule, where D is the training data set, which includes XY input-output pairs. Variational inference approximates a complex probability distribution, probability of W given D, with a simpler distribution Q theta. In some cases, mean field variational inference, every parameter is modeled by independent Gaussian distribution with mu and variance sigma squared. We use two losses. For variational layers, we train using a combination of elbow and cross entropy loss, and deterministic layers are trained using cross entropy loss only. During the prediction phase, the distribution is obtained by Monte Carlo estimators by sampling the weights from the posterior distribution. So we evaluate two uncertainty estimates, predictive entropy and BALD. Now some results. So we used moments in time data set, and we used a split. We split into the data set into 54 in distribution and 54 out of distribution classes. The audio is available for selected samples in both the categories. In these plots, we are comparing confidence measure from deterministic DNN models and uncertainty estimates from Bayesian DNN models to detect out of distribution samples. These are density histograms with area normalized to 1. DNN models indicate high confidence for both in and out of distribution samples shown in the left plot. The center plot is for MC dropout, a well-known Bayesian DNN approach. And the right plot is the proposed Bayesian DNN model with hybrid deterministic and variational layers. We can observe that Bayesian models provide higher uncertainty for unseen or out of distribution data, indicating reliable uncertainty estimates. In these plots, we are comparing confidence measure for true and false predictions from the DNN and Bayesian DNN models. We see that Bayesian DNN models provide lower confidence measure when their predictions are wrong, indicating more reliable estimates, whereas the DNN models provide high confidence even for false predictions. We also compared our proposed method with different data sets. In this case, UCF 101 video activity recognition as in distribution, and MIT dataset with video-only samples as out of distribution data. We see that both the uncertainty measures, predictive entropy and BALT, provide reliable uncertainty estimates which can detect in and out of distribution samples. And finally, the reliable uncertainty estimates obtained from the proposed method provides better accuracy AUPR and AUROC values, while providing reliable uncertainty estimates which can be critical in the real-world applications. The proposed Bayesian DNN model provides precision recall log improvement of 10.2% on MIT in distribution samples we have considered. So please drop by our poster number 34 for more details and more in-depth discussions. Thank you.
All right. Can you? All right. There is one question about the paper number 32. The question is the interpretation often requires deconvolution to retrieve the input signal. Can the presented deformer filter easily deconvolutable? I mean, my interpretation about this question is, I mean, here the interpretation often require deconvolution to retrieve the input signal. So the question is, can your deformable filter be easily deconvoluted? Sorry.
So the question is the deformation convolution.
I mean, I think that my question, this question actually asks whether you run the filter for the decoder independently, or the filter is somewhat related to the filters in the encoder.
Okay, so the filters for the deformation convolution, the deformation absence, is learned directly from the input and another filter. So our deformation abscess is based on that kind of mechanism, but with lower dimension, and we have a different mechanism to propagate the filters over the feature space.
I see. So does that answer say that you have separate filter for the decoder?
Yeah, we have a separate filter.
All right.
Thank you.
Another question from the floor? All right, I actually have questions for paper number 33 and 34 both, where actually some actions may not be correlated with some audios. I mean, the audio features may not be representative for certain kind of actions. How do your framework behave in that case? So.
Sure. I think this is the exact case where we want to target, where if one of the modalities is more reliable or more confident about its decision, then we want to rely on that decision. So it depends on the training data set, like audio for a given class. For example, if it's a bicycling sequence, and if there is an audio which is someone is singing in the background, And if we use that as a label, class label, then it will have higher uncertainty.
Okay.
But the video will have lower uncertainty. So you want to choose the one which has lower uncertainty based on
I see.
uncertainty estimate you.
Yeah, that is what exactly you want to do.
Yeah, exactly.
About
sorry. Yeah, please ask a question.
About the last paper, would it be fair to say that the application of the last paper could be used to detect like anomalies or maybe detecting fake news?
Sure, yeah. So uncertainty estimate can be used for different applications, yes. So these are all like valid applications. Anything out of distribution or not, any samples which fall apart further from the training data set is what we are trying to detect. So
okay, thanks.
Yeah, thanks.
So can you briefly answer my question? Sorry. Yeah.
Okay, so in the audio-visual event localization, our target is to find some co-occurrence between audio and visual segment. So if there is something audio missing or some not very strong audio signals, our method may be retrieve some wrong results.
I see.
Okay.
All right, let's thank speaker again.
So the next paper is non-local recurrent neural memory for supervised sequence modeling.
Hello everyone, I'm very delighted to present our work on local recurrent neural memory for supervised sequence modeling, which is joint work with Wenjie and other colleges from Peking University and Tencent. The key challenge in sequence modeling is to capture long-range temporal dependence in the sequence. For instance, suppose we aim to recognize actions through front input video based on only the skeleton information. It is very difficult to make the correct recognition by only sampling from some frames from the video. Only capture the temporal information of the whole video can we recognize the action accurately. However, typical sequence models like STM cannot perform explicit modeling of high-order information interactions between non-adjacent time steps. Hence, it has limited capability of temporal modeling. To address this limitation, in this paper, we propose a non-local recurrent neural memory network. As shown in the same example, our methods models four-order interactions between all time steps within memory blocks by non-local operation, and models global interactions between memory blocks by gated recurrent update. Besides, our model is able to learn latent high-level features contained between non-adjacent time steps and can be seamlessly integrated into existing recurrent sequence models. As illustrated in this slide, we build our model upon SDM backbone as an instantiation. Our model is the memory embedding MT for a block at segment K time steps. And in practice, we use a sliding scheme to select hidden states as the source information for memory cells to avoid potential information redundancy and improve the modeling efficiency. Here, the sliding window is designed to control the updating frequency of memory state. We consider two types of source information: the learned hidden representations by the LSTM backbone and the original input features. To distill information in current blocks that it was to return in memory, we apply multi-hot attention to model four-order interactions among source information in all time steps. Besides, to model the temporal consistency between adjacent memory blocks, we update the memory state in a gated recurrent manner, which is similar to the recurrent scheme of STM. Specifically, we incorporate the obtained memory state into the recurrent update of STM cell states to have refined quality via memory gate GM as shown here. The newly constructed state CT is further used to derive the hidden embedding HT of the whole sequence model prepared for the final prediction. To evaluate the generalization of model across the different tasks and modalities, we conduct experiments on two tasks: skeleton-based action recognition on the NDO dataset and the sentiment analysis on the text NDB test dataset. It should be noted that we opt for NTO dataset using only 3D skeleton joint information rather than kinetics based on RGB information to highlight the importance of temporal dependencies. We first compare our model to the basic recurrent models on NTO dataset into evaluation metrics CS and CV. The figure shows that high-order RM perform better than vanilla RM, which implies the necessity of the non-local operation, since high-order connection can be considered as a simple non-local operation in a local area. And our model also outperforms STM. Next, we compare our model to the state-of-the-art methods. Our model achieves the best performance under the same condition. Similarly, we perform experiments on MDB datasets to evaluate the model on the test modality. The figure shows that our model outperforms all other RM-based lines substantially. And our model also performs much better than the state-of-the-art methods under the same condition. We present a concrete video example with the action label working towards each other. It is quite challenging to recognize actions since it can only be inferred by the temporal variation of the relation distance between two persons in the scene. Hence, captured long-range dependence is crucial to recognize it. The standard STM misclassifies it as slapping at a person, where our model succeeded. Here is an example of sentiment analysis for IMDb dataset. This example is very challenging since the last sentence of the view seems to be positive, which is prone to misguided models. Our model is able to correctly classify it as negative where STM fails. In summary, our model can model long-range temporal dependence and learn latent high-level features. Also can be seamlessly integrated into existing recurrent models. For more detail into this paper, please visit our poster. Thanks for your attention.
The next paper is Temporal Attentive Alignment for Large-Scale Video Domain Adaptation.
Good afternoon, everyone. I'm Chen, a PhD student from Georgia Tech. I'm going to introduce our paper on cross-domain video understanding. Video understanding has been a popular topic in the past several years. Let's take a classification task as an example. In one data set, if we want to classify two actions, desk work and walk, we can simply train a model. However, this model isn't guaranteed to work on our data set, especially when overall distribution is very different. And the model trained using the second data set may be far away from the first one. This problem is called domain shift problem. Here we treat each data set as one domain, including source and target. To solve this, our goal is to convert and map the feature spaces of source and target domains into same or similar feature spaces. And then it'll be much easier to train one model to work on both domains. The way to achieve this is called domain alignment or domain adaptation, or abbreviated as DA. There already exist many works dealing with cross-domain vision problems, but most of them focus on images only. Video is a different story. Because video contains both spatial and temporal information, one is within frame and the other is across frames. By applying image-based DA, we can align the spatial feature space. However, there still exists domain shift in temporal feature spaces. Therefore, we need video-based DA to further reduce the overall domain shift. Unfortunately, it is still an underexplored area. Unlike images, there are not many approaches focusing on video-based DA. Moreover, there do not exist well-organized and large-scale datasets for investigating cross-domain video problems. The existing related datasets are too small to have enough domain shift to evaluate performance of DA approaches. A strong baseline with deep CNN can produce almost perfect accuracy even without DA. Therefore, we first collect two larger-scale datasets, UCF HTTP4 and Kinetics gameplay. More importantly, our datasets have much lower source-only accuracy, which means larger domain shift that's worth investigating. For our baseline, we adopt the current popular image-based, adversary-based DA, and then extend to our baseline architecture for videos by inserting temporal module using temporal pooling. The problem for this baseline is that the relation between frames is still ignored. Therefore, we first modify the temporal module. Inspired by TRN, we learn various local temporal features that encode relations between frames in different time scales, and then combine into a global temporal feature. And then we insert domain discriminators to both local and global temporal features so that we can directly align the temporal feature spaces. But it's still not enough. Directly summing up local features means aligning them with the same weights. However, actually all features contribute differently to the overall domain shift. Some have lighter domain shift, and some have more severe domain shift, and so on. So, direct summing up is not the best way. To solve this, we propose the domain attention mechanism to assign all local features with their attention weights that are obtained from the domain discrepancy. In this way, We can focus more on aligning those which have high contribution to the overall domain shift, achieving more effective domain alignment. For experience, first we check the existing data sets. There are only a few previous works, and a strong CM backbone can outperform even without DA method. So it means the saturated performance in this data set, and our approach can improve. For our proposed data set, first, the source-only performance shows our data set much more challenging. And second, since there's no existing benchmark, we extend several popular image-based DA for video as a comparison. Finally, by directly aligning temporal features with domain attention, we can further improve the performance. So this shows that for videos, how to effectively align features like encode temporal dynamics is much important than what DA method or loss functions to use. We also visualize the source and target distributions using t-SNE. The baseline framework cannot well align the distribution between different domains, even with DA. And temporal relation module can help the group source data densely, but not able to depth to target data. And our approach can achieve both. So to summarize, we first collect large-scale data set to facilitate video DA research, and explore how to effectively align spatial-temporal features, and develop approach to simultaneously attend, align, and learn temporal dynamics across domains. Finally, feel free to visit our poster and check the paper for more details. The code and the data are available online. Thank you.
The next paper is Action Assessment by Joint Relation Graphs.
Good afternoon, everyone. I'm Jia Hui, and I'm a master's student from Sun Yat-sen University, supervised by Professor Wei Shizheng. Now I'm going to present our work on action assessment. Action assessment is a task of assessing how well an action is performed. It is widely applicable to many real-world scenarios, such as medical treatment and sporting events. Different from recognition, assessment focuses more on detailed motion. Still, we don't assess the performance on each joint independently. We have to refer to the states of its neighboring joints. A certain joint motion pattern does not always indicate high skill. It can be normal in some cases, but a flaw in some others. Let's take diving as an example. Knee bending at the rolling stage is normal, when the ankle and hips are also bending. But a knee bending can be a flaw at the water entering stage, when the ankle and hips are stretching. Therefore, we analyze the interactive joint motion patterns within body parts instead of analyzing each joint independently. But how to represent the body part? Actually, since human skeleton structure is an undirected graph, we model the local joint relations through graphs. In particular, we build the spatial and the temporal relation graphs. The spatial relation graph relates joints within the time step. The edges are bidirectional, and self-loops are included. The temporal relation graph relates those across immediate time steps. Here shows the relations towards the left hip at time step t. And a single body part then can be modeled by a joint together with its neighbors on the relation graphs. But in fact, an action is regarded as well performed, not just because of its excellent local motion. It must also maintain good coordinations among joints. Therefore, we proposed a commonality module and a difference module for motion learning. The commonality module aggregates the general motion of each body part. And the motion difference module reflects the joint coordination, because small differences within a body part indicate good coordination, while large differences indicate poor coordination. Now let's look at the motion commonality learning. Here, we take the joint neighborhood around hip I as an example. The motion commonality module performs a graph convolution on the relation graph. So, hip I will first compute the general motion of its neighborhood. Here, H is the hidden state of all nodes on the graph, and A is the adjacent matrix of the graph. Before the graph convolution, each node has the local motion of a certain joint, forming H0. Then after the convolution, each node has the general motion of a joint neighborhood forming H1. The learning of the motion differences is in a similar way, only that we aggregate the motion differences rather than the general motion. Here, heap I compares its local motion to its neighbors, and then aggregates the motion differences through graph convolution. The relation graphs are not set still in our model. The edge weights are learnable. They indicate how much each joint is dependent to its neighbor's state when the model assesses an action. A large edge value indicates a strong joint dependency in assessment, which means that the decision on a joint is strongly dependent to the motion state of another joint. Our model achieves state-of-the-art result for action assessment in Olympic events and surgical actions. As our model gives partial score for each video segment, it is able to locate when an error occurs. What's more, we can further analyze the body part motion to show which body part has the best and worst performance. In conclusion, our method helps to achieve fine-grained action assessment, and it also helps to interpret the action assessment process, giving insights on how the model evaluates the action qualities. Thank you for listening. I'm Jia Hui, and I'll be looking for a PhD position. Please interview me at my poster, number 37. Thank you very much.
Okay, we start the Q&A session. If you have any questions from the floor, please approach the microphones. So I have a question on paper 35. So did you observe any case in which the long-term memory actually hurts your performance because you need to focus on really short differences and not the long-term ones?
It very depends on the data set, and our main idea of this paper is to learn the hidden high-order interactions between non-adjacent time steps, and our model learns the high-level features between non-adjacent time steps.
I have a question, actually. Yeah, I have a question for paper number 36. Yeah, well, the flow information is very useful to recognize the actions. Also, that information is pretty domain invariant. So, did you compare the performance with the flow-only features?
So, so this paper, like mainly using RGB frame, RGB information, and we consider flow can be a like good compensate information to RGB. So I believe if we use flow information, we can further improve the performance. But in this paper, we just want to focus on if we only have RGB information, how to adapt the do domain adaptation.
All right.
Thank you.
Okay, so a question on paper 37. So to my understanding, the graph convolution should already be able to compute the difference between the motion with the aggregation, with the convolution itself. So why do we need also to compute the motion difference separately?
Yeah, actually, in our modeling, the adjacent matrix set in our model is non-negative. So, so the motion difference module and the motion commonality module, they work differently. The motion commonality module will aggregate the general motion because it is just like a weighted sum. Then the motion difference module will aggregate the differences, and this reflect the joint coordination of the neighborhood.
Okay, so it's more about the representation rather than the operation itself, let's say.
I'm sorry?
It's more about the representation, so one has the differences while the other has sort of the absolute.
Yeah. Yeah.
Okay. Okay. Thank you. Thank the speaker again.
Right, it's now for the last group of the session. In the last group, we have only 2 papers. The first one is unsupervised procedure learning via joint dynamic summarization.
Good afternoon, everyone. My name is Ehsan, and this is a joint work with Zuenang. There exists a large number of instructional videos on the web. YouTube has more than 500,000 videos for tasks such as setting up Chromecast or performing CPR. Instructional videos provide great resources for automatic procedure learning, which is to learn the sequence of key steps in order to perform a task whose outcome could be used for teaching complex tasks to robots or building assistive technologies. Given a collection of videos of the same task, unsupervised procedure learning refers to discovering the sequence of key steps and localization of them in videos. This is an extremely challenging problem. First, we need to reconcile large variation in pose, illumination, actors, objects in videos. Moreover, different videos have missing or additional key steps with a slightly different ordering. Also, videos may have repetitive key steps, and often large portions of videos correspond to irrelevant background activities. In this work, we develop unsupervised procedural learning methods using visual data that handle missing and repetitive key steps and partially handle background actions. We develop efficient methods based on joint dynamic summarization of videos that have performance guarantees and outperform the state-of-the-art by 10% in F1 score. We also released Procel, a new multimodal instructional video dataset. The key idea of our work is that a dynamic model learned from time series representations of videos can capture key steps and their ordering. More specifically, in an HMM learned from videos, some of the latent states correspond to key steps and the rest correspond to background actions, while state transitions encode information about their ordering. Thus, our goal is to find a subset of states and assignments of video segments to them that will represent videos and follow the dynamic model. To achieve our goal, we develop a potential function on sequences of assignments that capture these 2 goals. This leads to maximizing a function that consists of sum of similarities between each video segment and its assigned key state, and sum of initial and transition probabilities in sequences of key state assignments. Here, beta is a regularization parameter. We treat a problem as maximizing a set function, fs, over all subsets of states of size at most k, and we run a greedy search algorithm that incrementally finds key states. At each iteration of the greedy, we use dynamic programming for function evaluation. Our method runs linearly in the length of videos and number of states. We also show that under some conditions on the dynamic transition model, our proposed function is approximately submodular, hence the greedy has performance guarantees. For evaluation, we have built Procel, a multimodal dataset of 47 hours of instructional videos from 12 diverse tasks with 60 videos per task that contain annotation of key steps in videos along with manually corrected speech transcripts. We have released the dataset for public use. We evaluated F1 score of our method against the state-of-the-art on INRIA and our Procel dataset as a function of the final procedure length. As you can see, our method in blue significantly outperforms other methods for majority of tasks. In particular, we observed the highest improvement for the task of CPR that contains repetitive key steps and clearly follows a dynamic model. Our method, however, didn't do as well for the task of change tire or change iPhone screen due to high visual similarities among key steps. We show that using the dynamic model, in fact, significantly improves the performance. Also, as we increase the summary size, our method is able to capture more ground truth key steps. We show that simply using off-the-shelf summarization methods improves the state-of-the-art by about 4%, and our joint dynamic summarization methods achieves an additional 10% improvement in F1 score. This shows the effectiveness of summarization methods for procedure learning. We also believe that procedure learning is a less subjective task than general video summarization, and would be important for more fair evaluation of different summarization algorithms. Thank you.
All right, next paper is Visual, the fine-grained spatial-temporal video similarity learning.
Hello everyone, my name is Giorgos Kordopatis-Zilos, and today I will present you our work for fine-grained spatial-temporal video similarity learning. This is a joint work between CERT ITI and Queen Mary University of London. Our objective in this work is to learn a similarity function that, given two arbitrary videos, calculates the similarity score between the two videos based on their visual content. The application scenario that we use in order to evaluate our method is video retrieval, where the similarity function have to handle several types of variations, such as near duplicate videos, complementary scene videos, and same incident videos. Several methods in the state-of-the-art extract CNN features for each video frames and then aggregate them to a video-level representation in order to measure similarity based on these representations. The major limitation of these methods is that they do not consider the spatial-temporal information during similarity calculation. Another common practice is to calculate the similarity between each frame pair based on their global frame representations and then apply a temporal alignment step to calculate similarity. The limitation of these methods is that they do not consider the spatial structure of video frames during similarity calculation. To this end, our goal is to address these limitations and learn a similarity function that respects at the same time spatial and temporal information of videos. We achieve this by calculating the frame-to-frame similarity that respects frame structure and use it in order to learn a video-to-video similarity function that considers the temporal structure of videos. In a deeper look in our method, given two arbitrary videos, we first extract the region-level features and then calculate a region-to-region similarity matrix based on their dot product. To calculate a single similarity score for the two frames, we apply a max operation over the target region vectors and followed by a min operation over the query region vectors. This similarity function is called chamfer similarity. Here are the similarity matrices generated from the comparison of all the frames in the query and the candidate video. Comparing our method with a baseline one, we can see that a lot of noise have been reduced and also many diagonal parts are more visible. In the second step, we provide the extracted similarity matrices to a video similarity learning network. This is a 4-layer CNN that captures the temporal structure in the similarity matrices with convolutional filters. To calculate a single similarity value for the two videos, we apply again chamfer similarity, and we implemented this by applying a max operation over the target video frames, followed by a min operation over query video frames. To train our network, we provide triplets of an anchor, a positive and a negative video, and we train it by minimizing the triplet loss function. We evaluated our method in several video retrieval tasks, such as near duplicate, fine-grained incident, action, and event-based video retrieval. In all of the examples, our method achieves very competitive performance, and in many cases, it outperforms state-of-the-art by a large margin. Finally, we provide some visual examples of query and target video pairs, the input and the output to the VSIL network, and the calculated similarity based on our system. It is noteworthy that the VSIL network has learned to extract meaningful temporal patterns from the similarity matrices, such as strong diagonals. If you have any question, please come by our poster. The code and models are available in GitHub. Thank you very much.
We don't have any question in the Slido system. So is there any question from the floor? Oh, yeah. For paper 39, is it necessary for the two videos to have the same number of frames?
Sorry, can you repeat the question?
The two frames should have the same number of frames, or how to?
No, it's independent entirely. You just compare the two videos, and it's not a constraint the number of frames that the video should have.
So how do you handle the different numbers of frames?
Due to the convolutions in the video-to-video similarity calculation, it doesn't need to provide a similarity matrix of a given size, because you have the convolutional filters that scans the similarity matrix. So
you mean the similarity matrix may not be diagonal?
Exactly.
I see.
Exactly.
So I actually have another question about your paper. The frame-to-frame similarity, is it invariant to the order of the frames? I mean, if we shuffle the frame orders, still the similarity is same?
Well, this is a very good question. In a perspective, from an outside perspective, it seems so, but we have found experimentally that because the regional vectors encodes the frame structure in a way that it is, let's say, bounded to the topology of the frame, then if you just shuffle the regions of the image, won't have the same output in the frame-to-frame similarity calculation.
I see. So can I understand, like, conceptually yes, but practically no?
Exactly.
Okay, thank you. For the paper for 30, is there another question? For paper 38, I try to understand the optimization framework. The objective function is defined on the multiple videos.
Yes, this is a joint summarization. From an optimization perspective, this is a joint subset selection.
I see.
And the goal is going to be to find a common subset from a big ground set of all the states. And we are going to also find out assignment of each of the segments to each of the states, but the sequence of assignments for each video is allowed to change slightly depending on the dynamic model.
I see. That joint summarization framework is defined on only two videos, or is it applicable to the multiple videos?
It's basically, in the experiments, we run it on whatever number of videos we have. It's basically 50 to 60 videos in the data set at the same time.
All right. Any other question? All right. First, thanks to the speakers. And this concludes the video and action understanding session. Thank you so much.